Welcome. This is where your journey into real networking begins. Over the next 60 lessons, we're going to build the mental models and practical skills that working network engineers actually use every day. And we're starting with a question that trips up a lot of people: OSI versus TCP/IP. By the end of this lesson, you'll know exactly when to reach for each one and why both still matter. So here's the roadmap for the next few minutes. We'll start by walking through the 7 OSI layers, what each one actually does, the devices that live there, and the protocols you'll recognize. Then we'll look at the TCP/IP model, which is only 4 layers and reflects how the internet was really built. After that, we'll line the two up side by side and finish with the part that matters most on the job, knowing which model to pull out when you're troubleshooting or talking with your team. Before we dive into the layers themselves, let's pause on a more basic question. Why do we even bother with models? Think about what actually happens when you open a web page. A packet leaves your laptop, crosses cables, routers, and fiber, and lands on a server halfway around the world. Electrical signals, MAC addresses, IP routing, ports, encryption, application protocols, all of it happening at the same instant. Nobody can hold that whole picture in their head at once, and that's the point. The fix is to slice the problem into layers, each with one clear job, each talking only to its neighbors above and below. That's the entire reason OSI exists. So here they are, all 7, stacked from the physical wire at the bottom up to the apps you actually click on at the top. Read it from the bottom. Raw signals become frames. Frames become routable packets. Packets become reliable streams with port numbers, and from there sessions, formatting, and finally, the application protocols you already know, like HTTP and DNS. Each layer trusts the one below it and serves the one above. And if the names won't stick, lean on the mnemonic, top-down. All people seem to need data processing. A bit corny, but it works. Now, here's the twist. OSI is the textbook model, but the internet was actually built on a simpler one. TCP/IP only has 4 layers. It collapses OSI's session, presentation, and application into a single application layer, because in practice, protocols like HTTP handle all 3 themselves. And it merges the physical and data link layers into one link layer, since whoever owns the cable usually owns the framing too. Same ideas, fewer boxes, and much closer to what engineers actually deal with day to day. So if we line them up side by side, the mapping becomes clear. OSI's top 3, application, presentation, and session, all fold into TCP/IP's single application layer. Transport stays as transport, network becomes internet, and the bottom 2, data link and physical, get bundled into the link layer. Same reality underneath, just described at a different level of granularity depending on how much detail you actually need. So which one do you actually use? In practice, you reach for OSI when precision matters, teaching, certifications like ccna or network quests, or troubleshooting where saying that's a layer 2 problem instantly tells a colleague where to look. TCP/IP comes out when you're dealing with the real world, reading RFCs, digging through Linux networking, or working in cloud and DevOps contexts where AWS and Azure docs speak that language. Senior engineers don't pick a side. They switch mid-sentence depending on who they're talking to. And here's where these models really earn their keep. When something breaks, you walk the layers. Is the cable plugged in? Does the device have a MAC and an IP? Is the port open? Is DNS resolving? Each layer gives you a small answerable question instead of one overwhelming, why isn't it working? You can go top down, starting from what the user reports, or bottom up, starting from what you can physically verify. Either way, you stop guessing and start eliminating. So, how does data actually travel down those layers? Each layer takes what's handed to it from above and wraps it in its own header. HTTP becomes the payload for TCP. TCP becomes the payload for IP. IP gets framed by Ethernet. And finally, it all goes out as bits on the wire. At the other end, the receiver peels those headers off in reverse order, layer by layer, until the application gets back exactly what was sent. That's encapsulation and de-encapsulation in a nutshell. And as data moves through each layer, it actually gets a different name. That's where PDUs, or Protocol Data Units, come in. At layer 7, we just call it data or a message, drop down to transport, and TCP calls it a segment, while UDP calls it a datagram. At the network layer, it becomes a packet. At the data link layer, it's a frame. And finally, at the physical layer, it's just bits on the wire. Using the right word in a troubleshooting conversation tells your colleagues exactly which layer you're working at. And that precision saves real time. And here's where all of this stops being theory. Open any packet in Wireshark and you'll see the layers stacked exactly as we described. The Ethernet frame on the outside with its source and destination MAC addresses, then the IP header with the real source and destination addresses and a TTL of 64, and finally TCP inside that, opening a connection to port 443 with the SYN flag set. Each indented block is one layer of encapsulation, and clicking any line highlights the exact bytes it occupies. That's the model made visible. So let's pull the threads together. Remember 5 things from this lesson. OSI gives you 7 layers of precision, while TCP/IP gives you 4 layers that match the code actually running on your machine. Reach for OSI when you're teaching or sitting a cert, and TCP/IP when you're reading RFCs or debugging real traffic. When something breaks, your first question is always, which layer is broken? Be precise with your vocabulary. Frame at 2, packet at 3, segment at 4. And encapsulation is just wrapping on the way down, unwrapping on the way up. That's the whole foundation. To make all of that stick, here's your one-page reference. Keep this cheat sheet handy. The 2 models side by side, the PDU names at each layer, when to reach for which framework, and the classic mnemonic, all people seem to need data processing. To lock the OSI order into memory top-down, screenshot it, pin it to your second monitor, whatever works. In the next lesson, we stop talking about models and actually follow a packet on its journey across the wire. And that brings us to the doorway of lesson 2, packet journey. We'll trace a single packet from your laptop all the way to a remote server, frame by frame, watching the layers we just studied come alive in real traffic. If this lesson clicked for you, head over to dargslan.com or the YouTube channel to keep the series going. See you in the next one.